Good morning, everyone. I hope you guys had a nice break. Just want to go over a couple of things before we look at the notes for today. First is that from a couple weeks ago, I think I gave back your test for Chapter 7. If you want to do recovery for Chapter 7 tests, same thing applies as previous tests. You can come in sometime either between now and Wednesday or today and tomorrow. Come in and do recovery, or come in and do corrections with your corrections for your test with the key. And then either this Wednesday or Thursday, you can come in and take a recovery for that Chapter 7 test. Hopefully between those 2 days, you can find a time to come, but if something doesn't work out and you need a different time today, you can let me know. We can talk through that. So, but Chapter 7 test, you can recover up to 79 for that test. So, second is that I graded and I entered in your FRQ quiz 1. Again, it's down to 50 points. It should be under your test grade, test column. I merged the quiz and the homework grade, so most of you earned full 25 points for your for the homework that's attached to that test grade, and so whatever is remaining is going to be your quiz grade. So I'll try to hand back your quiz grade, your quizzes, sometime next day or two. Now, if your overall test grade was under an 80, you can come in and do corrections for that quiz, and then retake up to cumulative 80%. Okay, so you can earn up to 40 out of 50 on that quiz grade. And if you're missing a homework, then you can make up all the homework that you're missing and still earn a 4 out of 5 points for each of the homework assignments. But most of you guys have already done them, so. But if your grade is low because of your homework, and you can still show me your homework. Last week or the week before spring break, the packets from limits all the way to curve sketching, first semester topics, those packet is also going to go in the grade book as a quiz grade. So what's between 28th and the 1st, that packet grade will go in as a quiz grade under the quiz column. So Friday, I checked pages 10, 11, and 12, and then over the break, I had you guys work on page 13 through 16. So tomorrow, I'm going to check all the pages 13 through 16. Just many of you guys were not here on Friday, and then I don't want to check the day after the break. However, because of that, we have that little bit of backlog from these assignments. I'm going to check that as well as pages 1 through 4 in the packet today. But I think we're going to get through a good portion of those 4 problems. We'll get through maybe 2.5, and really just only have a page and a half to 1.5 problems to finish up. So tomorrow I'm going to check Thursday and Friday. If you weren't here on Thursday, I'm sorry, if you weren't here on Friday, I'm going to check pages 10 through 12 as well as 13 through 16. Okay, so what's coming up is we're going to be focusing on these FRQ topics, particle motion, Riemann sums, antiderivative word problems, differential equations. And then next Tuesday, we're going to have a 2-problem quiz just over Riemann sums and differential equations. And the same thing applies as the previous quiz. All the homework up to that point between this week and next Monday will be 25 points. And then the FRQ quiz will be 25 points. I'm going to merge them together to be a 50-point test grade. And after that, we're going to focus on multiple choice topics. And we're going to try to get through first and second semester, just multiple choice problems. And then the Tuesday after next, we'll have multiple choice pre-test that will be out of 50 points or 25 points rather. But then that's going to be supported by the homework that you did. And then Thursdays, part 2, second semester topics with calculators will also be 25 points, but it'll also be supported by your homework. So both of this will cumulative will all go in as a 100-point test grade. So 25 points from the first multiple choice, 25 points from second multiple choice, 50 points from the homework. Okay. And then after that, that's going to bring us, oh, and then these quizzes will just be 30 minutes apiece. It's only 8 problems per day. But this week is all going to be kind of messed up because of FRQ schedule, sorry, because of end of course schedule. So we're only going to be like, be in a class about 35 minutes or so. This pretty much for this week. After that, your AP exam week is going to start. But our AP exam is not until the second week. So that first week, we're just going to be working through FRQs from previous years, the most recent ones. So from 2016 to 2021, we'll work on those, and all this will go in as a quiz grade as well. And then AP exam for us is the Monday, May 9th. And after that, we're just going to be, if you have to do recovery or help sessions or late assignments, we'll take care of that in the remaining 3 weeks of school. Okay, any questions with the calendar or what's coming up? Okay, let's go to your packet. Guys, now looking at the calendar for this EOC week, I think Tuesday and Fridays are actually going to be the ones where the testing will be extended. So I may have to adjust it to be Wednesday and Thursday, not Tuesday and Thursday, just because Wednesday we're going to have potentially less than 30 minutes for some of the classes. But yeah, all the classes will be cut too short on those days. So I may have to change. I'll confirm, but I think I'll have to change that multiple choice from Tuesday to Wednesday. So it'll be Wednesday and Thursday instead of Tuesday and Thursday. Yeah, just because Tuesday and Fridays, those testing days will be a little bit longer. I think bio and algebra 1, 11th grade lit and algebra 1 will be longer on those days. Okay. All right, so let's look at particle motion and Riemann sums. I'm just going to go through a couple of these formulas as reminders, and then we can kind of look into number one. So as a reminder, we know velocity is the derivative of position. So x prime of t can represent velocity. It could be v of t. It could be dx over dt. Acceleration is the second derivative of position. You can see acceleration as a of t. It can also be represented as v prime of t, the first derivative of velocity, dv over dt. But yeah, acceleration can also be the second derivative of position. So you may also see it as x double prime of t. We know derivative is going to allow us to get from position to velocity to acceleration, but we can also do the antiderivative procedure to make our way up the chain. So the antiderivative of acceleration will bring us up to v of t. Or you can write it this way, or you can also write it as the integral from a of t dt will bring us to v of t plus c. You can also think of it as position as the integral of v of t, or you can think of it as the integral of v of t dt will bring you up to x of t plus c. Total distance is the absolute value under the velocity function. So total distance is where all the accumulation of areas, the distance traveled, the displacement are all converted to be positive values. So any regions above and below the x-axis are all converted to be positive areas, and we just total them up. Okay, average velocity. Think of average velocity as the average value theorem for velocity function. You can also think of average velocity as the change in position over the change in time. Thanks. There's a packet there. You can pick up. Just like over here, right? Average velocity is change in position over change in time. Average acceleration is change in velocity over change in time. So look at how, if we're thinking in terms of slope, average velocity, we don't touch velocity function, right? And in average acceleration, we don't touch the acceleration function. It's just change in velocity over change in time. Okay, displacement of position. We know the antiderivative of v of t will bring us up to position. If I plug in the upper and lower bound, it's x of b minus x of a. We can also rearrange this into something that is useful for finding final position. Final position is initial plus displacement. We'll use that a lot. Okay. We can also take this first theorem and adapt it for one derivative down. So the integral from a to b of acceleration will bring us up to v of b minus v of a. Okay. Increasing, decreasing speed versus increasing, decreasing velocity. Increasing, decreasing speed, we look at velocity and acceleration and we compare their signs, right? If the velocity and acceleration have same signs, then we know that particle is experiencing increasing speed. If velocity and acceleration have different signs, then we know that that particle is experiencing decreasing speed. But increasing, decreasing velocity is a little bit different. We don't compare signs, we just look at acceleration. And this is a little tricky because we see velocity, so we want to automatically think that this is the same thing as positive velocity, but it's different. So increasing velocity is not the same thing as positive velocity. We don't look at velocity, we look at acceleration because the word increasing kind of changes what we're asking for. It's the rate of change of velocity, which is just acceleration. Okay, so let's look at number one here. Okay, we have a table of values with given time, given velocity, and given acceleration. Okay, a car travels on a straight track. During that time interval from 0 to 60 seconds, the car's velocity is measured in feet per second. And acceleration is feet per second per second. They are both continuous functions. Now, because acceleration is continuous, that means that velocity is also differentiable, because acceleration is a derivative of velocity. So it says they're both continuous, but it's also indicating that because acceleration is a derivative of velocity, this also indicates that v of t is differentiable. Because they say acceleration is also continuous. Okay, the table shows the values of these functions. Using appropriate units, explain the meaning of the depth integral from 0 to 30. Of v of t in terms of the car's motion, then approximate using trapezoid approximation with 3 subintervals determined by the table. Okay, so we know that this notation indicates that this is total distance. So for part A, we can say the depth integral from 0 to 30 of absolute value v of t is the total distance traveled between 30 and 60 seconds, right? That's the formula that we see here. Total distance is the depth integral of the absolute value v of t between our 2 time intervals. Okay, second part of A, use trapezoid approximation with 3 subintervals determined by the table. So we know that trapezoid area is 1/2 width, height 1 plus height 2. Okay, 3 subintervals between 30 and 60. Remember, we can subtract the time intervals to get the width, and then the height is going to come from the velocity values. So we find the difference in these time intervals. 35 minus 30 is 5. 50 minus 35 is what? 15. And then the width here is 10. Okay, so our width is going to come from those numbers, and the height is going to come from the velocity numbers. A slight adjustment we have to make is that we have to convert all these heights to be positive, because the absolute value tells us that we're going to treat every area under the velocity graph as positive values. So here's our formula for trapezoid approximation. 1/2 width, height 1 plus height 2, 1/2 width, height 1 plus height 2, and then 1/2 width, height 1 plus height 2. Use the calculator. We started with feet per second, so if we find the area or approximating the depth integral, then we know our units will change, right? We're always getting rid of the denominator of our units if we're taking the antiderivative. Okay, that's the calculator portion there. Now, if this was non-calculator, you could leave your answer like this. Okay, but if it's calculator, then you can just enter it in. Okay, part B. Says using appropriate units, explain the meaning of the depth integral from 0 to 30 of acceleration. So we know the integral of a of t will bring us up to v of t, and then we can plug in upper and lower bound. So we see this formula here, right? This is just basically rearranging of first theorem integral of a of t will bring us up to velocity. We plug in upper lower bound. So we can do that for our problem as well. We can convert a of t to velocity to v of 30 minus v of 0. And that just means the change in velocity, right? So v of 30, according to the table, is negative 14 feet per second. The car is starting at negative 20 feet per second when the timer starts. And if we subtract those two, we can find out the difference that the car experiences between 0 and 30 seconds. So if these are the velocity at these time periods, then the difference between them is just the change in velocity between the time periods. Okay, part C, between 0 and 60 minutes or 0 and 60 seconds, is there a time where v of t is equal to negative 5? Can we guarantee that? So, okay, let's look at our table here. We see velocity goes from negative 20 to negative 30 to negative 20 to negative 10 and then to 0. So we know that our velocity is continuous. So we know that if it's continuous, that this car is not going to be able to jump or skip over a velocity if it's going to have to go past it. So we see the key is between 35 and 50 seconds, right? You see negative 10 and 0. If the velocity is negative 10, and if it goes 0, then it has to cross negative 5 at least once. Right? And that's IVT. So we can say that by IVT, because velocity is negative 10 at 35 and velocity is 0 at 50, and our target is negative 5, we know our velocity has to reach that point somewhere. We can guarantee it because our velocity is continuous. So that all feels very wordy, right? You can say it in a number of ways, but this is the most efficient way that College Board will accept. So I want to kind of show that to you. So we say it this way. We say, okay, we target the two time periods that has the lower and higher value that we're looking for. So we know that velocity at 35 seconds is negative 10. Negative 10 is less than negative 5, and negative 5 is less than 0, and 0 is what's experienced at 50 seconds. So this kind of shows that relationship that College Board is looking for if it's IVT problem, to show that, okay, I'm testing a value below, I'm testing value above. It's going to be guaranteed to live between those two endpoints that I've identified. And our velocity is continuous. So that's also a condition for IVT. Then there must be a time t where velocity is negative 5. Okay, so this is the most, you can write it out in different ways. It's going to feel a lot wordier if you do, which is not wrong, but this is just the most efficient way where you'll be able to earn full credit on College Board. If it's IVT problem, you don't have to use as many words this way. Part D says, very similar wording. Is there a time t when acceleration is equal to 0? What do you guys think? So that is where it's easy to make that conclusion, right? We look at acceleration and say, well, there's no guarantee that acceleration can be 0 because it never reaches that point. It looks like it never reaches even negative values, right? It's all positive values. But we know that the way that they design AP problems, you're not going to be able, chances are part D is not going to be easier than part C, right? Chances are it's going to be a little trickier, a little bit more involvement. So that's also kind of a red flag too. If you're working through an FRQ problem on the AP exam, and part D feels too easy. It could be the right way, but you kind of want to look at it a little bit more closely. It's like, am I missing something? It feels too easy to just be an IVT problem where you look at these numbers and it's all above 0, so it can't be 0. So there's actually something else. We're not going to be looking at this acceleration. We're going to be looking at the velocity line. Okay, what do you know about acceleration? Acceleration is the what of velocity? Derivative, right? Derivative is another word for what? Slope. So acceleration is equal to 0 is also meaning what? Yes, slope of v of t is equal to 0. And if I want to guarantee a slope of 0, that's a different theorem, right? What theorem is that? Okay, not mean value theorem, but what's the theorem that guarantees a slope of 0? Rolle's theorem. So this is asking us to see if we can spot that difference there, that yes, IVT is not going to be able, it's going to be inconclusive, right? We're not going to be able to guarantee it with IVT, but with Rolle's theorem, all we require is continuity, differentiability, and 2 velocity values being what? Being the same. And we can spot 2 velocity values being the same. So if velocity at 0 is negative 20, let me show that what graph that graph could look like. And then it goes down to negative 30. And it goes back up to negative 20. Then between those 2 points, the graph has to connect and go down and come back up. In that process of going down and coming back up, it's a smooth curve. It has to reach a slope of 0. If there's a slope of 0 for velocity, that's where acceleration is equal to 0. So yes, we can't guarantee using IVT, but we can guarantee using Rolle's theorem. Okay, so we write it out this way here. Let's see, like easier for you to read here. Okay, so by Rolle's theorem, since velocity is continuous and differentiable, now it doesn't say that velocity is differentiable, but it did say that acceleration is continuous. But since acceleration is the derivative of velocity, then continuity for the derivative graph is the same thing as differentiable for the original graph. So continuous on the closed interval, differentiable on the open, and the third condition is also met. V of 0 and V of 25 share the same velocity. So if it's going to start at negative 20 and dip down and come back up to negative 20, there's got to be a place where that velocity slope is going to experience 0. And velocity slope 0 is the same thing as acceleration 0. Okay, let's look at number 2. All right, temperature of water in the tub at time t is modeled by a strictly increasing. So that's something that's going to be, we're going to need to refer back to that when we're looking at one of the parts here. Twice differentiable. That just means it's a smooth curve. The derivative can be taken twice. It's not going to be just a straight line. It's going to be a smooth curve. Where W of t is measured in degrees Fahrenheit and t is measured in minutes. at time t equals 0, the temperature of the water is 55 degrees. The water is heated for 30 minutes, beginning at time t equals 0. Values of Wt at selected times for the first 20 minutes are given. So the whole range is between 0 and 30 minutes. The table only gives us between 0 and 20, so that typically means that something else in the problem later is probably going to define what's happening between 20 and 30 minutes. Okay, but the table is only showing the first 20 minutes. We see at time t equals 0, the temperature of the bath water is 55 degrees. Then you see it kind of increasing over that 20-minute time period. Okay, part A. Use the data in the table to estimate W prime of 12. So W prime of 12, that's the derivative of the Wt, but we don't have a function to find the derivative. So the best thing that we can do is to estimate it using what? Find the what? Slope, right? Slope is just a fancy, derivative is a fancy word for slope. So if I want to find the slope, that will give us the closest slope to what's happening at 12. What points do we want to use? Yeah, choose the closest. All right, the closest time period obviously is not going to be a great estimation because ideally we'll want something a little bit closer, but we're kind of restricted to the table. So the closer we are, the less room things can change. So our best approximation is going to find the closest to our target. Okay, so change in temperature over change in time. Okay, so W prime of 12 is just the change in temperature over the change in time between 9 and 15 seconds. Now, if it was asking for W prime of 10 or W prime of 11 or W prime of 13 or 14, it would all give us the same slope, right? Because all we have are the two order pairs. So, you know, this is obviously not very accurate because we don't have time periods that are closer than what we are given between 9 and 15. But notice this is a unit change. All right, this is the rate of change, temperature over time, so degrees Fahrenheit per minute. So our best guess is that at 12 minutes, the temperature is rising or increasing at a rate of 1.107 degrees Fahrenheit per minute at 12 minutes. Okay, part B. Use the data in the table to evaluate the integral from 0 to 20 of W prime. Using correct units, interpret the meaning of integral from 0 to 20 of W prime in the context of this problem. So we can apply first theorem, right? We know first theorem tells us that the integral of my derivative will bring me back up to my position level. So we know that W prime is going to rise up to W of t, and I can plug in my upper and lower bounds. So it's going to end up being W of 20 minus W of 0. All right, so this is first theorem, right? Integral of W prime. That derivative is going to disappear. It's going to rise up to W of t, and then we plug in upper and lower bounds. So that's the same thing as W20 minus W0. If you think about it this way, this is a lot easier to interpret, right? This is the temperature of 20 minutes minus temperature of 0 minutes. So that gives us the change in temperature over that 20-minute period. So we know the temperature starts at 55. It's going to eventually rise up to 71. So over that 20-minute period, the temperature is going to increase 16 degrees. From 55 to 71. Okay, part C. Between 0 and 20, the average temperature is given by this average value theorem here. Integral of W of t over that time period, 1 over b minus a, integral from a to b of W t dt. Use left Riemann sum with 4 subintervals. So we're going to use Riemann sum for this portion here to approximate the area under the WT graph, and then we can take that number and divide it by 20 at the end. So left Riemann sum between 0 and 20. So let's do that. Subtract each of the time intervals. That will give us the width. All right, 4 minus 0, 9 minus 4, 15 minus 9, 20 minus 15. And then for each of the heights, we want to choose the left interval, right? So for the first interval, you're choosing between 55 and 57, but left Riemann sum tells us we want to choose the left height. So 4 times 55 will be the first area. Second area will be 5 times 57, then 6 times 61, then 5 times 67. So width times height, width times height, width times height, width times height. But that's the accumulation of all the temperatures. We still got to divide it by 20. Right? So if we get a number that's like, like 240, that's not quite right? Average temperature is not going to be 240 if there's going to be 55. It's going to be probably somewhere between 55 and 67, which is like 61, right? That could be a good guess, and that's where we're going to end up with, right? So don't forget about that 1 over 20 that you got to multiply through or divide by to get that average temperature. Okay. Does the approximation overestimate or underestimate the average temperature over these 20 minutes? So what do you know about the graph? The graph is what? Strictly increasing, right? So if it's increasing, and if you want to do left Riemann sum, if you attach the left height of every rectangle to the graph, you can kind of visually see that, oh wait, this is going to be an under approximation because the gaps I experience is going to be below the curve. So the area of these rectangles is not going to be as much as the area under the entire curve. So our estimation is going to be an under approximation because our graph is increasing and we're using left Riemann sums. So these are things that you don't really want to memorize, right? You really just want to be able to sketch a graph and just convince yourself, right? The graph is increasing and there's right Riemann sums. You can visually convince yourself that, okay, all my rectangles are peaking above the curve, so it must be an over approximation. All right, part D. Part D says between 20 and 25 minutes, the function W that models the water temperature is given by W prime. Based on a model, what's the temperature of the water at time t equals 25? So we know that the change in temperature between 20 and 25 minutes is going to be modeled by this. So if I take the antiderivative of that W prime, then that's going to bring me up to W of t, right? And also we have the temperature at 20 minutes. So if I add on the accumulation, the change in temperature, I can figure out the exact temperature at 25 minutes. So this goes back to this formula that we've been seeing in the past with particle motion, right? Final value equals initial plus displacement. It's the same idea here. Final temperature equals, or starting temperature plus the change in the accumulation of temperature over that time period. So if we take the integral of W prime, we can figure out the change in temperature between the two time periods. So we're trying to target temperature at 25 minutes. We know the temperature at 20 minutes, right? That's the edge of our WT table. And the only thing we have to figure out is how much does the temperature change between 20 and 25 minutes. If we can find the change in temperature in the 5 minutes, we can tag it onto the temperature at 20 minutes, and we can find the total, the resulting temperature at 25 minutes. Okay, make the calculator do this for us. Again, if you see the variable t on paper, you're always using variable x in your calculator. And what mode should we always be in? Always radian mode, right? It's just safer that way. Never play with degrees, just always be in radian mode. That way, any trig is not going to be thrown off because you're in a wrong mode. So the temperature at 20 minutes is 71 degrees. We accumulated the temperature change in the 5 minutes, which is 2 degrees. So it's going to rise 2 degrees after 20 minutes, and we add those two together. We know the temperature is going to be 73 degrees 25 minutes in. Okay, number 3. We can get started with some of the one of the homework problems that you're responsible for. So I'll be checking pages 1 through 4. I think we'll be able to get through a good portion of page 3. Okay, does anybody still need this? Okay, number page 3 here. Okay, particle moves along the x-axis so that its velocity v is given by v of t. The graph of v is shown here between 0 and square root of 5 pi. The position of the particle at time t is x of t, and its position at time t equals 0 is x of 0 equals 5. Okay, find the acceleration. So we know acceleration is the derivative of velocity. We can work it out by hand. We can also make the calculator do it for us. This is easy enough. We don't want to go through chain rule. You can. Sine of u becomes cosine of u times u prime. If I want to find the acceleration at 3 seconds, you can do it out that way, or remember you have that Math 8 feature in your calculator, right? If you do Math 8, you can type in your velocity function and then make the calculator evaluate the derivative for you. You want to find the rate of change of the velocity at 3 seconds. Okay, so if you work it out by hand and plug it in, or make the calculator do the Math 8 and derivative feature for you, you'll get the same result. Part B, total distance. Total distance, you know, is going to be the definite integral of the absolute value of v of t. Definitely make the calculator do the work for you here. The way you get to the absolute value is you do math 9 first. Math 9 will take you to the definite integral notation. And if you do math number, you'll see ABS, and that will help you get to the absolute value bars. Math number ABS. I think 1.702. Part C, find the position of the particle. So position of the particle. We know position is the antiderivative of velocity. And we also have a starting point for my position. So I can go back to that formula that I've been using, right? Final position equals initial plus displacement. So if I want to find the position at 3, I can start at 0 and then figure out how much change has occurred over that 3-minute period. Make the calculator find that integral for you. You know the position at 0 is 5, so he starts at 5 and then he travels 0.773 units, and then add those together, you get 5.773. Okay, now part D is going to be an EVT problem. Let's talk about this here. It says between 0 and 5, 0 and root 5, find the time at which the particle is furthest to the right. So basically want to figure out when is, so we definitely test endpoints and test critical points. And this is the velocity graph. So we know the critical points will be at the x-intercepts, right? So you can make the calculator, you can make the calculator find those intersections for you, which is fine. But we can also work this out by hand because it seems complicated, but right, when is sine equal to 0? Right, sine is equal to 0 at, if you think about unit circle, it's all variations of 0 and pi, right? 0, pi, 2 pi, 3 pi. So we know that sine is going to be equal to 0 when t squared is equal to 0, pi, 2 pi, 3 pi. If I want to solve for t, I just take the square roots. And conveniently, square root of 5 pi is our endpoint, so we can just test these values, right? Find the positions at each of these time periods. But it says furthest to the right, so technically we want to test all of them. Just the relative maxes, right? So we know that it's going to be above, then below, then above, then below, then above. Sorry. So we only need to test endpoints and relative maxes. So it's just 0, root pi, root 3 pi, and root 5 pi. Okay, so we use the same formula for all of them. Initial position plus displacement. And then you find each of the positions, and the one that's furthest to the right is the one that has the largest position value. So at time t equals 3 pi, okay, furthest to the right. So tomorrow I will be checking pages 10 through 16 and for your previous packet because of the Thursday, Friday before break. Those of you guys who are here already checked your 10 through 13, but I may just ask you to show me again just so it'd be easier just to go through again. And also be checking pages 1 through 4, but we already did pages 1 through 3, so just one more problem on page 4. I'll send out a reminder this afternoon, and the keys are all on my website.